All right, gang, here we go. Chem 1, Unit 4. This is part 2. We're talking about electron dot structures. All right, so a couple of things we need to touch base on. We have, so we talked about ionic and covalent bonds. Electron dot structures only apply to covalent molecules because they're sharing electrons. All right, and so electron dot structures in general are just a way of representing what your molecule looks like and kind of visualizing what's going on with it as it actually bonds to one another. All right, so we need to talk about this first concept: single, double, and triple bonds. All right, a single covalent bond happens when you're just sharing one pair of electrons, and it's represented by a line. Okay, double covalent bond is when you have two pairs. I know it's mind-blowing right here. Be two lines, and a triple covalent bond is three pairs. Okay, so it'd be three lines, right? And you know my drawing is just off of it. They should all be. Doesn't really matter how long they are. All right, maybe 1, 2, 3. Okay, so essentially, just another way to think about this. This would be two electrons, right? Because it's one pair, and so this guy would be 4 electrons. All right, and then a triple bond is 6 electrons, right? Because each pair has 2. All right, so we can just multiply 2 by, however many pair of electrons we have. Okay, so electron dot structures, a method used to keep track of electrons in a compound. All right, so we already talked about the bonds. Bonds are represented by lines. Electrons are represented with dots. All right, here's a bunch of rules. Okay, so pause the video, jot these down real quick, and so here we go. Least electronegative atom always goes in the center. A lot of times your molecule is written so it's the very first element. That makes your life easy. All right. However, hydrogen can sometimes come first, especially in an acid, but it can never be in the center because hydrogen can only make one bond because it only wants 2 valence electrons to be like helium. All right. They're going to make bonds with the lone electrons, right? So electrons are almost always going to come in pairs, okay? And your job is to satisfy the octet rule on each atom by adding lone pairs to their bonds, okay? So remember, your octet rule means that each atom wants to have 8 valence electrons. Now, this doesn't apply to hydrogen because hydrogen wants to be like helium, and helium only has 2 electrons. Okay, if there's a charge, you need to account for that by adding or taking away electrons. So remember that if your thing has a positive charge, that means it lost electrons. So you're going to take electrons away if you see a plus. If it's negative, that means it gained electrons, right? Because electrons are negatively charged. Okay, so it's a little bit backwards, all right? And then finally what you have to do is you're going to check the number of electrons you've used in your drawing to the number of valence electrons that are available. All right, so that's kind of like the general rules here. All right, so we're going to do 3 examples together. All right, so first up we have NH3. Now first thing I do is just write out how many valence electrons I have. So I have nitrogen and I have 3 hydrogens, okay? And I'm going to add up how many valence electrons they have. So nitrogen has 5 valence electrons, and I know that because it's in group 5A, right? And then, so it's got 5, and then hydrogen, I've got 3, and each one has 1 electron. So I've got 3 hydrogens, so I put 3 here, and then so I'm going to add those guys up, 5 plus 3 times 1, so that gives me 8 valence electrons. All right, available, 8 valence electrons. All right, so I'm going to put NH3, okay, and so I got to decide which one's going to be in the middle. Well, I already know hydrogen can't be in the middle, so it has to be the nitrogen. All right, so I'm going to go ahead and bond this guy up to my hydrogens here. All right, so I put that in the middle and just attach everything else to it. Okay, now, so then we have to think to ourselves, okay, now we're going to satisfy the octet rule and everything. So hydrogens, remember, hydrogens, they only want 2. So this hydrogen has 1, 2 from this bond, right? This hydrogen has this bond. So that hydrogen's good, that hydrogen's good, that hydrogen's good. And now we got to think about the nitrogen. Well, nitrogen, how many electrons does it have around it? Well, it's got 1, 2 from that pair, 4, and then 6. But it wants 8, so we're going to put 2 dots here, 1 for each of those electrons that are attached to it. And so therefore now it's got 8 electrons around it, right? It's got 3 bonds, right? And then a lone pair, right? So 1, 2, 3, 4, 5, 6, 7, 8. So now it's satisfying the octet rule. Okay, so it's got 3 bonds and 1 lone pair, right? And we call this a lone pair because it's a pair that's all alone. Okay, all right, so it's using 8 electrons, and we had 8 valence electrons, so we're good. So this would be the electron dot structure for NH3, ammonia. All right, Now let's try CH2O. All right, so we've got a carbon, 2 hydrogens, and an oxygen. We're going to figure out how many valence electrons we have to work with. Carbon's in group 4A, so it's got 4. Hydrogen's got a valence of 1, and then oxygen has 6. All right, so this would be 4 plus 2 times 1 plus 6, so that's 12 electrons. So we got 12 valence electrons to work with. So we're going to decide which one's going to go in the middle. Well, the least electronegative one goes in the middle, except for hydrogen. Carbon's the least electronegative, so it's going to go in the middle. And then we're just going to attach everything else to it. So we've got 2 hydrogens. All right, it doesn't really matter where we put it. All right, so we could do those, and then we'll put an oxygen. Now we've got to think about this. All right, and we've got to add up now we've got to think about our octet rules, right? So hydrogens are good to go because they only want 2. Carbon's going to need another 2. It's the same setup as the nitrogen. But now life's a little bit more complicated because we've got oxygen down here, and he wants to have 8, so we got to give him an octet as well. All right, so now the octet rule is satisfied, but we got to think about how many electrons we've used. So we've used 2, 4, 6, 8, 10, 12, 14. Right now we've used 14 electrons in our electron dot structure, but this guy only has 12 electrons, right? We've only got 12 valence electrons to work with, so we've got a problem, right? So when this occurs, we're going to substitute 2 lone pairs for 1 double bond. Okay, so imagine this. If I take this and I get rid of these 2 lone pairs and these 2 lone pairs, and I add in a double bond between the carbon and the oxygen right here, right? Well, now how many electrons have I used? Well, I've used 2, 4, 6, 8, 10, 12, right? I've used 12 electrons here, okay? And the carbon, well, and then we also make sure everything's still following the octet rule. Carbon has 2, 4, 6, 8, so that's got 8 electrons. And oxygen has 2, 4, 6, 8, so it's also got 8 electrons. So between those two, we're still following the octet rule, and we've only used 12 electrons. So therefore, this guy here has to be the electron dot structure for CH2O, right? Let's try ammonium NH4+. So first of all, figure out our valence electrons. So we've got nitrogen, we've got 4 hydrogens. All right, we're going to add those guys up. Nitrogen is in group 5A, so it's got 5 valence electrons, and 4, 1, right? Now, so there's 9 valence electrons to work with. All right, 9 valence. All right, but we've got this plus. Now remember, that plus means that it's got a charge of +1, which means it lost an electron. So we're going to subtract 1 off of this. So really we've got 8 valence electrons. All right, but they're not really valence. It's more like 8 electrons for our dot structure to work with. So don't call it valence. That was a mistake. All right, so now we're going to write this guy out. We already know nitrogen's going to go in the middle, and we're going to attach everything else to it. So we got hydrogens everywhere. All right. NH4. All right, now think about our octet rule. Our hydrogens are happy because they each got 2. Nitrogen wants 8, so 1, 2, 3, 4, 5, 6, 7, 8. So we're at 8, and we wanted 8 electrons, right? Now, one thing we have to do to show that it's a charge, when you draw a electron dot structure that has a charge, you're going to put a bracket around the whole thing and then write the charge outside in the top right. So ammonium has a charge of plus, right? 1+. So we're going to put that plus up there in the top right corner right there. All right, NH4+. So there's our electron dot structure for NH4+, which is ammonium. All right. Now, resonance structures are things that happen when it's possible to write 2 or more valid electron dot structures. So that means the octet rule is followed, and that also means that all of our we've used just the right number of electrons. All right. So these are called resonance structures. And so if you have a molecule that has more than one possible valid structure, okay, then we have to write resonance structures out. And now in order to do that, we're going to write each resonance structure by itself and then separate them with a double-headed arrow. And so that'd be like an arrow that looks like this. Okay, double-headed arrow. All right, and that's to separate those resonance structures. And now the trick to this is that when you have a resonance structure, there isn't a particular structure that actually exists. It's really a hybrid of all the different structures that exist. All right, so let's try carbonate here. All right, so this is CO3 2-. All right, so valence electrons, we got carbon, we've got 3 oxygens. We're going to add those valence electrons up. Carbon is in 4A, so it's got 4 valence electrons. Oxygen's in 6A, so 3 times 6. So we have 4 plus 3 times 6. Well, 3 times 6 is 18 plus 4. So we got 22 valence electrons. All right, but it's got a charge of 2 minus, so that means we're going to add 2 more electrons that we have to work with. So that means we have 24 electrons we have available to play with in our valence or our electron dot structure. All right, least electronegative goes in the middle. All right, and then we're just going to attach all of our oxygens around the outside. Give everything an octet. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. All right, so we've got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6. So everything follows the octet rule. All right, now let's see, make sure we haven't used too many electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Uh-oh, we've used too many electrons. Remember, when that occurs, that means we're going to add a double bond. So we're going to get rid of 2 of our lone pairs, and they have to be off the same thing. Oops. Whoa, hello. All right. Means they have to be off the same thing. So we're going to put this guy like this. And then, so now we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And it's got a charge of 2 minus. So we got to put the brackets, add the 2 minus. So there's our electron dot structure of carbonate. Now, when we're looking at this, like you might have said, well, why did I choose that oxygen to put the double bond on it? Well, really, I could have chosen any of these oxygens, right? So really, I have a resonance structure where this double bond could be on any of these 3. So my resonance structure, I could have one resonance structure that's like this, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4. So I could have that guy going on, right? So that would be a valid resonance structure, right? 2 minus. Yeah, it's exactly the same thing. Or we could have a third one where the last one is the double bond is down here instead. So like this, single, 1, 2, 3, 4, 5, 6, 1, 2. Oop, we don't. Oh shoot, I need to erase those. Was moving too fast with my dots. All right, so we'll erase those above the carbon there. All right, so there is my 3 valid resonance structures for carbonate. Okay, each one of is equally valid, and really in nature, no single one of these exists. It's kind of a combination between all 3 of them, where like this double bond is delocalized. It's separated and shared between these 3 different bonds, and you don't need to be able to draw these for these classes, or for our class, but I'll just go ahead and draw this in real quick, and then oxygen, and then so you've got like this delocalized double bond that's represented by dashes between those 3 different guys there. All right. Last little bit here in this part is bond dissociation energy. Okay, bond dissociation energy is the energy it takes to break a covalent bond. All right, so you've been lied to in biology. You were told that breaking bonds releases energy. You were probably told that when you talked about ATP. That's not true. What actually happens is that in order to break a bond, you have to put energy into it. And so the stronger the bond, the more energy it takes to break it. Imagine trying to karate chop a board, right? If it's a really thin bond, a piece of balsa wood, it'd be really easy to karate chop through it. Now, if it's a piece of maple, that thing's going to be a lot harder. And imagine if you've got like 5 or 6 stacks of maple wood together, that makes it even more complicated. All right, so the more the bond dissociation energy you have, the stronger your bond is. Okay, and it's pretty easy to imagine triple bonds are stronger than double, and double are stronger than singles. Just imagine just having 1 piece of wood is a single bond, 2 pieces of wood is a double bond, 3 pieces of wood is a triple bond. All right, so but why do you care? Well, look at this guy here. You've got ethane. All right, ethane burns at about 1955 degrees Celsius. All right. That's still pretty warm, but it's not too terribly warm, okay? Especially when you compare it to acetylene, burns at almost 600 degrees higher. And the only difference is it's got that triple bond instead of that single bond. All right, so ethane, we burn propane and ethane in our barbecue grills outside, but then we use acetylene for welding, to actually melt metal and get them to stick together and form new metallic bonds. So anyway, so this bond dissociation energy is a very important concept. All right, but essentially what you need to know is that it's the energy it takes to break a bond. Triple bonds take a lot more energy than double bonds, which take more energy than single bonds. And that's about it for this unit. Next video, we'll talk about Vesper theory, to talk about the three-dimensional organization of molecules. It's very exciting stuff. Anyway, do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.